Hi there. In the first video in this series on Laplace transforms, we had said that a significant application of Laplace transforms is the ability to solve differential equations. And we can take a differential equation and convert it into an algebraic equation, and we can easily solve. So this video is going to illustrate that process. So to solve a differential equation using Laplace transforms, we just go through these 4 steps. So the first one is to rewrite the differential equation in terms of Laplace transforms. So we take each term of the differential equation and then write the Laplace transform of it. And that includes needing to write the Laplace transform of the actual derivative itself. So we'll see how to do that just now. And then the second step is to insert the initial conditions which are given as part of the problem. We substitute that in. And then the third step is to now take the algebraic equation that we have and then solve it. And then we get everything to be in terms of the Laplace transform. And then the last step is to now take the inverse of the Laplace transform, and then we get the actual solution of the differential equation like that. So the whole process is illustrated through a simple example, and that will become clear as we go through these different steps, how it actually works. So the first thing that we need to understand is that we need to find the Laplace transform of a derivative. And what does it mean and how does it look like? So we want the Laplace transform of the derivative, that's f prime t. So as was previously done, we always go to the definition. Laplace transform is the integral from 0 to infinity of e to the minus st dt, and now we have f prime t here. So we essentially integrate this, and we have to integrate it using integration by parts. So if we just remember the general formula for integration by parts, so we have the integral of u dv is equal to uv minus the integral of v du. We're integrating from 0 to infinity, so that's from 0 to infinity, and that's also from 0 to infinity. So one thing is going to be u, and one thing is going to be v. So here we'll choose this to be u, f prime t, and we'll choose u to be e to the power est, so that's u, and then dv will be f prime t dt. So u will equal to e to the minus st. So that means that du is going to equal to minus s e to the minus st dt. And then now we'll have dv equal to f prime t dt. So if we integrate this, then we get v is just equal to f of t. So we now put all of this into our Laplace transform. So Laplace transform of f prime t is now equal to, firstly, uv. So we have e to the minus st times v. So we have e to the minus st times f of t. And this is integrated from 0 to infinity. And then now we have minus integral from 0 to infinity of v du, so v is f of t, and then we are multiplying this by du, so that's times minus e to the minus st, well, the minus, and the minus here is going to give us a plus. And now this s, I'll just write it outside of the integral since it's a constant here. Then we have what's left, which is e to the minus st dt. So the Laplace transform of the derivative f prime t is now equal to, so this first integral, these bounds, so we substitute that in. So if we substitute in infinity as t goes to infinity here, so even though this f of t will go to infinity, this e to the minus st will go to 0. And we assume that this constant s is big enough such that this whole term will approach 0. So we have 0 inside here. So that's the first term. And then we have, putting in 0, e to the power 0 is going to be just minus 1. So we're going to have essentially minus f of 0 here because of the negative for the second boundary, and then we have f of 0, so since t is 0. Then we have plus s, and now look at this integral. This integral is just the Laplace transform of f of t. Remember that I'll just write this here on the top, the Laplace transform of f of t. The definition is integral 0 to infinity f of t times e to the minus st dt. So that's it. So this term here is just the Laplace transform of f of t. So what this means is that we can remove this 0. So the derivative, the Laplace transform of the derivative is just minus f naught, okay, the function where t is equal to 0, plus s times the Laplace transform of that function. So this is a significant piece of information, and we can even use this to get the second derivative. So the second derivative is just the derivative of the first derivative, and if we were to put that in, we have the Laplace transform of the second derivative of t. So now this is, instead of going to be f of 0, it's going to become f prime 0, then plus s times the Laplace transform of f prime t. And f prime t, Laplace transform of that, is what we had already shown here. So we can take this and put this in here. So when we do that, we get the Laplace transform of the second derivative at t is equal to minus f prime naught plus s into, okay, we're going to have minus f naught, that's the first term, then plus s times the Laplace transform of f of t. So if we just expand that out, what we get is that the Laplace transform of the second derivative of t is equal to minus f prime naught plus s, and minus times the plus will give us a minus, so we can just write that. And then s times s gives us s squared. So we have plus s squared times the Laplace transform of f of t. The whole objective was this was to express the derivatives just to be in terms of the Laplace transform of the function. You can see that we have the Laplace transform of the derivative, and now it's been put in terms of the Laplace transform of the original function. Similarly, the Laplace transform of the second derivative has been put in terms of the Laplace transform of the original function, and that is what is going to help us to solve the differential equation. Now we can illustrate that with the example. So let's just say now that our differential equation is that f prime t minus 2f of t is equal to 4. Remember that the objective of the solving the differential equation is always to determine what f of t is equal to. That is always the point of solving a differential equation. So remember that the first step was to take the Laplace transform of each term. So that's what we're going to do. So that means that we take the Laplace transform of this derivative, and we take this Laplace transform of this term, and we take the Laplace transform of 4. So that's what we need to do. And the Laplace transform of the derivative we showed just now is minus f naught plus s times the Laplace transform of the original function. Minus this 2, we can bring that out. And the Laplace transform of f of t and the Laplace transform of 4. So if we just compute all these different Laplace transforms, we have now minus f naught, that remains the same, and then we have plus s times the Laplace transform of the function, then minus 2 times the Laplace transform of the function itself. Then the Laplace transform of 4 is just 4 over s according to our standard transforms which we had derived in the previous videos. So we can put in our boundary conditions, right? Our initial conditions, sorry, and we can state for this original differential equation, perhaps an initial condition is that f of 0 is equal to 1. Basically, the function takes on the value 1 when t is equal to 0, so you can substitute that in. So we have minus 1 plus s times the Laplace transform of the function minus 2 times the Laplace transform of the function equal to 4 over s. So I take this minus 1 to the other side and I get 4 over s plus 1. So that is just merely s plus 4 divided by s. So I put that in here. So now I also take out this Laplace transform as a common factor here. So I get the Laplace transform of the function of t, this is my common factor now, into, I have s, and I have minus 2, and this is equal to this s plus 4 over s. So I can just solve for the Laplace transform. And if I do that, I get that the Laplace transform of the function is equal to s plus 4 all over s into s minus 2. So to find the original function, right, all I need to do now is to take the inverse of the Laplace transform of this s plus 4 all over s into s minus 2. And that will give me my function, f of t. So that's all I need to do. And to find this term, I simply need to just use partial fractions. So we are now going to split this expression using partial fractions. So we have s plus 4 over s into s minus 2. So this is equal to a over s plus b over s minus 2. So we had spoken in the previous video about using the cover-up rule as a shortcut to finding these kind of coefficients a and b. So that's what we're going to use. So a is going to equal to, firstly we block off s here, then what we're left with is s plus 4 over s minus 2, and what we do is we take the limit as s approaches 0, because we just have s here, so there's no number associated with it, so it's just 0. So when we substitute that in, we get 4 over minus 2, which is just minus 2. We can do the same thing with b as well. So b is equal to, firstly we block now s minus 2 in this original expression, and what we're left with is s plus 4 all over s. And what we do is we take the limit as s approaches 2. So what that gives us is 2 plus 4 is 6, 6 over 2 is 3. So our expression s plus 4 over s minus 2, what we're doing is we're taking the inverse Laplace transform of this, and this is equal to minus 2 over s, because that's what a is equal to. And then we have b, which is 3. So we have 3 over s minus 2. And we are taking the inverse Laplace transform of these expressions. So when we do that, we find that this is equal to essentially just minus 2. That's the inverse Laplace transform of 2 over s using our standard transforms. And then we have 3. And then we have s1 over s minus 2. So using, again, our standard transforms, this is just e to the power 2 over t. And what this corresponds to is our function. We can see that the inverse Laplace transform of this expression is the function of t. And we have now the function of t is equal to this expression here. So what this means is that this is the solution to the differential equation. And this is a very powerful technique. So just to summarize it once more, what have we done? We have our differential equation. Our original differential equation was, we can just write it here on the top quickly. It was f prime t plus 2f of t is equal to 4. And the purpose of the differential equation is to solve f prime t is equal to something. And to do this, what we do is we take the Laplace transform of each term of the differential equation, and then we substitute in our initial condition. Our initial condition was we had seen that f at 0, t is equal to 0 is equal to 1. We substitute that in, which is here. And then we solve for the Laplace transform as a function of t. And then we see that it was equal to some expression. We then decompose that expression to be in terms of partial fractions, such that we had individual terms with which we could take the inverse Laplace transform, giving us our original function as the solution to the differential equation. So thank you very much for watching.